So recording in progress now, and we are working again on the prediction model today. But it's going to be a good revision also because we will work first in this course, fitting a regression line. And then based on that fit, we will respond to the questions which are mentioned here. You see one by one, determine the equation of regression line. This process is the same like we did last time. Next process, what is the slope of the regression line? You know very well, and I will definitely respond to each and every question here, and you will have your recorded lesson also. Now, this one, let's read it. What is it saying? Because you should also be able to figure out what is it requiring from us? What is the data about? Like that chemical engineer that I told you about, he was discussing about the emissions from the industries, how much like Weber or whatever was the gases were emitted. And I asked him, for how long did you take the observations? Because without observations, we cannot predict it. He told me that they kept on taking the observations for the emissions from industry for almost 1 week. And based on that, he predicted something. Now we have over here an observed data provided to us. Based on this observation, we will be first fitting a regression line, and then we will predict the data for some things which is not available here. So let's read it. The National Weather Service uses a chart to determine the wind chill factor at various wind speeds. Wind chill is the cooling effect caused by wind blowing on the surface. This phenomenon explains why you can feel colder on a windy day than on a calm day. So wind speed does include the chill factor. That's what is an like assumption. And then they observed it also. Have you normally checked the weather in your mobile apps? And it tells you that this is the temperature, and then it additionally tells you feels like. Remember the feels like? That's the basis. The wind speed makes it feel higher or lower. If it's a calm, windy stuff, then you will feel the feel will almost be equal to the actual weather, the temperature. But if it's really windy, then the temperature can be below the actual temperature. The feel can be below the actual temperature. That's what it is saying. So the following table shows the air temperature in degrees and the corresponding wind chill factor, the temperature in degrees in Fahrenheit that it feels like. So feel and the wind temperature, both are there. Let's see. So air temperature, 40. The wind chill factor, 30. That means it's windy. Then air factor, 35. The feel, 24. It's really windy. Like normally I've seen over here, if you will see in Tyler, the difference can be 3 to 4 degrees. But if it's that much a big difference, it's definitely a windy space. 30 to 17, 25 to 11, that's a lot. Now, let's determine the equation. And now it's a mathematical part, easy thing, the thing that we did last week also. Let's go to Desmos here. In Desmos, I will remove this thing from here because this is something that we were working on last week. And we will bring in a table here. Remember, how did we bring in the table? With the plus sign, enter the table there. And what is the data? What do we have there on the table? We have there a 40. And for the 40, the value of y is 30. Let's keep on adding the values. I will increase the size a little bit to let you see it better. I'm entering these values here. For 40, it's 30. For 35, it's 24. Do you remember how did we brought the points in view by changing the scale? I will do the same thing over here. From 19, I'm gonna bring in the x to somewhere like 40, and the y from 0 up till 40 again. Now I hope the points will be clearly visible to us. Okay, so 40 and 30, that's fine. Do you remember how did I bring in these points for the scale in view? You don't know how did I change the scale? I put for x and y both from 0 to 40. From 0 to 40. For x and y both, I use the scale from 0 to 40. Use the same thing and then keep on adding the points and let me know if you have the same thing visible on your plot or not. Then 30 and 17, 30 and 17. Then we have 25 and 11. Then we have a 20 and a 4. And then we have a 15 and a negative 2. So you see all the points popped over there? We just missed one point, which is negative 2, because I didn't cover the negative 2 in my x scale, y scale. So let me like zoom out a little bit, and now it's there. Got it? So what are we supposed to do? These are the observations. And we are now going to put here regression line. Remember how did we do it? I will now be saying and writing both the things over here in your canvas. Reminding you again, what keys did we use? We used the key shift plus 1. Sorry, not plus 1. Shift and negative sign. That's what we used to bring the underscore. So I will go back here, and while typing in here at this place, I will simply type in a y and then shift and minus. Shift and minus will take the cursor down, and I will type in there a 1. Got it? Then I will use the right arrow key. Cursor will go back up. Then I will use the shift and this tilde over here. This tilde over here. Shift and that sign will bring in this curly line, the tilde over there. Now, what we are going to do, we are putting in a straight line, equation of a straight line. So I will put there m and then x underscore 1. M and then x underscore 1. And then I will again hit the right arrow key to take the cursor back up. Then I will use the plus and then V. And we have a straight line. This straight line is showing us the regression line fit on this observed data. So we are trying to predict now the weather with its actual observation compared with its regression model, the regression line that we have fit over here. And what is the equation of this line? You do have the values of A and B with you, do you? Do you have the values of M and B with you in decimals? And the value of M is 1.2914. Value of B is what? Negative 21.5. Agree? Negative 21.5. So let's bring in the same information over here. It's saying as a first part, determine the equation of regression line. So what is the regression line? Y. Let me use some. Okay. So the regression line is y equals, what was the equation? 1.29143, 1.29143 minus 21.5143. 5143. Good question. If you want to get exactly the things as accurate as possible. You can put all the decimal places. Otherwise, 2 decimal places fine for me. 2 decimal places fine for me. If I'll be conducting this course in college or university, I will say 4 decimal places. But for you, 2 decimal places are good enough. Got it? Tell me. 1.29143 and then 21.5143. Got it? Now, second question, what is it asking you? What is the slope of the regression line? What do you think? Exactly. I heard the right thing from there. Who said it? Rosenberg? Good point. Good job. So the slope for the M is 1.29143. Good. And so, what does it mean in context of the problem? What do you think? What will I write over here? What does it mean in context of the problem? Now that's where I need your expert response. Tell me. What does it mean? I will type in here. I need your views. Tell me. Huh? What do we mean by this factor? What do we mean by the slope? Say again? The rate of change, exactly. That's a rate of change, but rate of change is a general concept for the slope. Here we do have a context. And the context was how much is it changing with an air temperature? How much is the field changing? How much change do you observe in the field of the temperature based on the actual temperature variations? So that's what I will mention here. Is it writing something there? Yes. Good. Yes. Why not? I will do that. And here I will bring it up here. And while doing that, is it better?
Yeah.
A lot better?
It's gone.
Where is it? It's gone. All the way gone. Instead of getting back, it's here. Okay, so now, again, sorry, here. Now, the slope here means a unit change in the field of temperature based on a unit change. I know it's going bad, but I will fix the change.
Yeah, here.
I'm fixing this well also over here now. Temperature fixed. Here, better. And if I'm doing the same thing and the word, it's a lot better. Based on the unit change in actual temperature. In actual temperature. Make sense?
Yeah.
No? I heard one no here.
Can you leave it there?
Yeah, I will leave it here. Don't worry about that. I'm trying to fix it down there somewhere. Here, so that we can have a look on this. Overall. Better?
Yeah.
So now we have the response for the slope. That slope is telling us what do we need to explain in the context. Now, mark my words. The words that I have used here, try to use similar stuff of the words whenever you are explaining something in context to a given problem. In context to a given problem, whenever you're using or trying to explain the slope, try to use the variables provided in the problem. Try to use the variables mentioned in the problem and use those words same way. Now, what's the next question?
When is the dependent variable active?
Exactly. So what is the dependent variable access, intercept, and what does that mean? So which variable have we considered here as a dependent variable? Why? But what was that? The field or the actual temperature? Look at the data that the way we have entered. What did we enter as the next? The actual temperature or the field? Look at that. We have mentioned here as X, the actual temperature. And the field over here is entered as the Y. And Y is always the dependent variable. X will be the independent variable. So that means if I'm considering here my air temperature is an X and the wind chill factor for the field is my Y, I can put it also over here. I will try to erase this shift in the thing from here. So I'm saying this is an X and this is a Y. Independent and dependent, both variables explained.
Okay.
Now, question, what is the dependent variable though?
What is the dependent variable?
What is the dependent variable? Dependent variable over here is the field or the chill factor. The chill factor temperature. Got it? So what is the intercept mean here? What do we mean by the intercept? Do we have a y-intercept? Go ahead, Carol. What will we mean by the intercept here on the axis? Yes. Looking at the plot, let me bring up the plot back again over here. That's the plot. So where do you see the y intercept? 21 point something, or this b negative 21.51 is the intercept. That means if we have a zero temperature, the actual temperature is 0, the field will be negative 21 point something Fahrenheit. Make sense?
So we write the negative 21 number.
We will mention the negative 21 as the intercept, which is the field or the chill factor at the zero temperature. At 0 degrees, the field will be negative 20 in that windy place, wherever it is taken. Make sense? So you will mention that thing over here yourself, the intercept, which is the temperature at 0 degrees actual. Intercept is the field in degrees. It will be field in degrees. Thank you for mentioning that. Field temperature in degrees is going to be negative 21.143. I believe that was 514. So I will just mention 21.51. Make sense? 21.51 is the field. Okay, use the equation of regression line to estimate. Now, this is the prediction part. That's what I told you in the beginning, and that's what the chemical engineer was also working on. When he's saying estimate, this word of estimate is prediction. So we're going to estimate the temperature, the field of the temperature in degrees when the chill factor for a 32 degrees Fahrenheit a day with a wind speed of 20 miles per hour. So what are we looking at now? We are looking at 32 degrees as a value of x. This value of x, we will substitute it in the equation and solve it the way always, like you can use a calculator or anything, or you can use your Desmos plot and just locate the 32 here. You see, when you hit or point on the line with your cursor and hold the shift key there, hold the not the shift key, the mouse arrow key or the touchpad left key, hold it there, move it and take it to 32. How much is the value for 32? 19.811 is your prediction or your estimate for the given value of 32 degrees. That's how you do that. So just by moving the mouse pointer or by pointing with your finger on that curve, we got the y hat. What is that? Y hat is always considered, this y hat is always considered as an estimated value. Okay, you use the y hat as an estimate. So y hat is what? 19 point or something. What was that?
19.8.
Thank you. 19.81 is the y hat. Got it?
Yeah.
That's an estimate. That is an estimate. And if it will be different from the actual temperature, the difference is called a residual. The difference will be called what? Residual. Did you notice something in Desmos? Let me bring it up here again. You see this? It's saying residuals. Residuals are actually the difference between your observed data and the estimated data from the regression line. If I will hit this plot button in Desmos, look at this. I just hit that plot button and it brought the red dots over here. These red dots are telling me the difference between the estimated value and the observed value at every single point here. Like I'm using now this, there's a slight difference over here between the green dot and the black line. That difference is a residual. And when we were working on this same thing last week, there was a big difference on some points also. Wherever the curve and the line, like over here, wherever the curve and the line will be slightly different from each other, that gap will be called the residual or the error of estimation. Okay, this will be more clearly visible if you will try to plot the curve where you're using an exponential function or you're using a quadratic function. Over there, you'll definitely be able to see that, observe that. Okay, so that was the main thing, prediction. Now, for you, can you tell me what will be the estimated value from the same plot? I'm waiting for it to appear. Hold on. The same question that we were working on here. Let me bring it up back over here. What is it? Okay, so I will suggest you to work on